energy changes in physical and chemical processes. This is a Form 4 topic. In this video, we review how the topic was tested in Chemistry Paper 2 for the year 2024. Stay tuned. Part A. State the meaning of the term standard molar heat of combustion. I want us to take note of the word standard, because as we shall be awarding marks, you will be able to take note of the importance of that word. So in this section, the examiner expected the candidate to define the standard molar heat of combustion as the heat or the enthalpy change. The heat or the enthalpy change that occurs when, of course, when 1 mole of a substance, burns completely. Instead of writing burns completely, somebody would say burns in excess oxygen. So it is the heat or enthalpy change that occurs when 1 mole of a substance burns completely in air. But I had indicated that we need to take note of the word standard. So without mentioning at standard conditions, then the examiner would not award the 1 mark for the definition. So for us to award the 1 mark, standard conditions were to be mentioned. Let's now proceed to part B, which basically tested the Hess's law of constant heat summation. So we are told table 5 gives the standard enthalpies for 3 reactions. So if we look at these 3 reactions and going by the definitions of the various enthalpy changes that we learned in class, reaction 1 can authoritatively be called the molar heat of combustion of hydrogen. But because we are also forming 1 mole of water from its constituent elements, that is hydrogen and oxygen, reaction 1 can also qualify to be the molar heat of formation of water. Moving to reaction 2, we can call this the molar heat of combustion of silicon, because we are burning 1 mole of it in excess oxygen. Again, this can also qualify to be called the molar heat of formation of silicon 4 oxide. Reaction 4 involves burning, of course, completely 1 mole of silicon 4 hydride in excess oxygen, and we get silicon 4 oxide and of course water. So this reaction 3 can only qualify for the molar heat of combustion of silicon 4 hydride. Now, the associated delta H, or the enthalpy changes for the various reactions, are also given here in kilojoules per mole. Now, the examiner went ahead to inform us that silicon and hydrogen react as shown in the following equation. So we have 1 mole of silicon solid reacting with 2 moles of hydrogen gas to give 1 mole of silicon 4 hydride, which is a gas. Now, having studied the table plus the extended information given down here, let us now go ahead and have a look at the questions that were to be answered based on the table. The examiner expected us to calculate the enthalpy change for the reaction that involved formation of silicon 4 hydride. Of course, we are supposed to get all the information from table 5. Let us therefore get back to table 5 and also have a look at the reaction that the examiner is referring to here. Here comes our table with the 3 reactions which we've taken time to go through very conclusively, and the equation that the examiner wants us to have a look at is down here. So we are supposed to use these values to help us calculate the enthalpy change for this reaction. And this is where now we apply the Hess's law of constant heat summation. Dear learner, we did a very conclusive video on the same. The video is titled Hess's law simplified. Kindly, if you have time, you can refer to it for more information on what we are about to do. So in simple terms, we are supposed to look at the 4 equations that are here, 3 in the table and the 4th one here. And then, according to Hess law, we are supposed to draw an energy cycle diagram using the 4 equations. And in that video that I've just mentioned, we said that the simplest thing to do is to examine the 4 equations and look at the one, identify one that is able to be used to derive the other 3. And you agree with me? The equation given here actually is the one that can derive all the others. So we shall use it as our main root from which the other subroots are gotten. So if we start at the point of silicon, we see equation 2 can be derived. So let's go ahead and do so. So downwards from silicon, according to equation 2, we can get silicon 4 oxide. Here, according to equation 2, and the heat change involved here is negative 911 kilojoules per mole. Now, equation 1 can be derived from hydrogen, so we shall also do so. We go down and we get water. But then you see that equation 1 tells us that only 1 mole of hydrogen is involved. But if you look at our equation here, we have 2 moles. So it therefore means that the negative 286 kilojoules that we have for equation 1 has to be multiplied by 2, so that we take care of the 2 moles that are here. Finally, we have reaction 3, that we can derive from down here. Going down like that, and of course we shall balance now water with a 2. The heat change involved for reaction number 3 has been given as negative 1517 kilojoules per mole. So the only missing heat change here is for our reaction given, and we can represent it as X. So this now becomes our energy cycle diagram, and by Hess law, we see that X kilojoules per mole, if you add to negative 1517 517, because this becomes our root 1 of arriving at the end point. Of course, here is our initial point. So we have two options. We can go through x and negative 1517, or we can go through the dual that involves silicon and hydrogen. By Hess law, the heat involved in the two roots must be equal. So you simply equate these to minus 911 plus, of course, 2 into negative 286. With this relation, we are now able to get our x. And x is given by negative 911 here plus 2 into negative 286, and then we shall add 1517 on both sides so as to eliminate it from the x side. If you have a good calculator, x, which obviously is the heat change involved in the reaction given down here, would be positive 34 kilojoules per mole. So this is what was expected to be calculated in question 6 part B. It is awarded 3 marks. So negative 911 would give half mark. 2 by negative 286 was awarded 1 whole mark. Addition of 1517 was half a mark, and the final answer is half. Of course, we ignored the units, but we want to tell the students that if you have to put them, make sure they are correct. Of course, K is a small k and J is a capital J. We proceed now to part C of question number 6. Part C was demanding that we determine the amount of heat change that would occur when 1 kilogram of water is formed. So with this again, we have to refer to the heat of formation of water that has been given in table 5. If we look at table 5, we see that the molar enthalpy of formation of water is negative 286. I want you to take note that here we are forming only 1 mole of water, which should be equivalent to 18 grams. The question is asking us about 1 kilogram. So we can easily relate 18 grams to 1 kilogram versus the amount of heat involved here. So we know that 18 grams of water, the formation of 18 grams of water involves negative 286 kilojoules per mole. So here, the question is asking us about 1 kilogram, which must be, of course, converted into grams. We would now relate those two. And through simple cross multiplication, we would do 1000 multiplied by negative 286, and then we divide by 18. I'm getting a value of negative 15,889 kilojoules. Now, it is 1 mark, so a half for the cross multiplication and division, and a half for the answer. Now, other than this value, if your calculator gives negative 15.888, negative 15,888.9 kilojoules, that would also qualify to be a correct answer. We also had 15,888.89. That would depend on the number of decimal points that a student would wish to express the answer to. And with that, we proceed to section D. In section D, we are informed that heating value or the calorific value of a fuel is the amount of heat released when 1 gram of a substance undergoes combustion. So we are told to calculate the heating value of carbon and hydrogen, of course, using the information given below here. So the first piece of information we have is when you burn 1 mole of carbon, don't forget this is 12 grams. In excess oxygen, to give carbon dioxide, the enthalpy of combustion has been given as negative 393 kilojoules per mole. Now, when it comes to hydrogen, heating 1 mole of it, which is equivalent to 2 grams, will be accompanied by negative 286 kilojoules per mole. Now, the examiner has told us that when we are talking about heating value, the amount of substance is supposed to be only 1 gram. Don't forget, for carbon, we have 12 grams producing that amount of heat. And for hydrogen, we have 2 grams producing this amount of heat. But for the heating value, now these masses must be related to what? To 1 gram. So now for carbon, the argument would be so easy. If 12 grams of it produces negative 393 kilojoules per mole, how about 1 gram? So we would have how much energy? This is 1 multiplied by negative 393, and then we shall divide by 12. We get an answer of negative 32.75. Now here units are key, so we shall express them in kilojoules per gram. Remember, we are burning only 1 gram. It's 1 mark, half for that, and half for the final answer with the units. So if units are missing or if they are wrong, then you don't score the 1 mark. Moving to hydrogen. Now we also argue out that if 2 grams are able to produce negative 286 kilojoules, how about 1 gram? Cross multiplication gives 1 by 286 divided by 2, and we get negative 143. Again, the units are key, kilojoules per gram. Half for the relation there and a half for the answer. We proceed to the final part of question 6, and that is part E. We were informed that 3 metals here, V, W, and X, displace copper from its compounds. So the examiner expected us to describe an experiment that can be carried out to arrange the 3, of course, in order of their reactivity with copper. And we were given a substance to use for that exercise, and it was aqueous copper 2 sulfate and a thermometer. So this would simply involve calculation of the heat of displacement. So how do you do it? What is the procedure? The first one would be, we would place equal volumes of copper 2 sulfate that has been given, and we do this in 3 separate beakers. We put that in 3 separate beakers because remember, we have 3 metals here. So that would give us the first mark. Once we have done that, now to each beaker, we would add, of course, excess of each metal powder. So, instead of talking of adding excess of each metal powder to our separate beakers, a candidate would replace this with add the 3 metals until blue color of copper 2 sulfate fades completely. So those words would replace the step number 2 for 1 mark. Then lastly, we would say that the reaction with the highest temperature reading, or the beaker that has the highest temperature reading, would be for the most reactive metal. Would be for the most reactive metal. So the second highest temperature you record would be for the next metal, and of course the lowest temperature would now represent the least reactive. So that would award ourselves the last mark, totaling 3. And on that note, we end our short video, where we have reviewed thermochemistry as tested in paper 2 of the year 2024. Stay with us for more of such insightful reviews.